Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad, India. So, the session we are going to study here, methods of determining slope and deflection. So, the course outcome and Bloom's taxonomy related for this session here it is. Deflection, apply the knowledge of theory, course outcome 4, and Bloom's taxonomy level is level 4. And here there are various methods determining the slope and deflections. So there are 3 methods here in order to find out the deflections. Let us recapitulate what is the concepts behind this, what is the slope and deflection. If we consider a simply supported beam is fixed on a fixed supported at the ends. Before applying the load, the beam becomes straight, and after applying the load, the beam will be bent, deflected. Point load here. The load can be a point load or uniformly distributed load, or it can be uniformly varying loads, or combination can be the point loads and uniformly distributed load, point loads and uniformly varying load, or UDL and UVL combinations. When these loads are applied, there will be deflection. Those deflections here can be calculated by using the double integration method. Second one is moment area method and Macaulay's method. These are the 3 important methods to find out the slope and deflection of a beam at a sections. Now, in the case of, yes, there are 3 methods. The first 2 methods, that is double integration method and moment area method, are used for single loads, and whereas Macaulay's method is very important method for multiple loads, highly useful for multiple or several loads. So in the case of double integration method, we know the equation, that is m equal to moment equation, moment and radius of curvature equation, that is m equal to ei times d square y by dx square. So where dx square by dx square becomes that m by ei. If we integrate first this equation, then what will happen? Dy by dx comes. The dy by dx is nothing but a slope. And the slope equation, if we integrate, then deflection equation can be observed. That is y. So when we integrate the first equation, that means dy by dx equal to m by ei plus constant of integration, that is C1. That is C1 constant of integration can be calculated by using boundary conditions. Let us see here. First integration, dy by dx equal to m by I times x plus c1. If we integrate again, that is the dy by dx is the slope. If we integrate further, second integration, y equal to m by I times x square by 2 plus c1x plus c2. If we want to get the value of deflection, we need 2 constants, c1 and c2. For slope, we need only 1 constant, c1. So this constant of integration can be, these constants can be calculated by using boundary conditions. That boundary, after calculating c1, substitute back in slope deflection equation, and use another boundary condition to find out c2. After knowing C1 and C2, substitute this C1 in equation, slope equation, and substitute C1 and C2 in deflection equation. Those equations indicates the slope and deflections. That is the methodology of double integration methods. Let us begin with this double integration method. How to find out the slope and deflection of a simply supported beam carrying a point load at the center. The point load is acted at the center. Okay, at the center. Now the beam having the length of the beam, the span of the beam is L. It's simply supported beam, and having a AB is the length, and point load W is acted at the center. As the load is symmetrically applied, the reactions RA and RB are equal. RA equal to RB. That equal to W is shared by two supports. That is W by 2 and W by 2. And the maximum deflection can be observed at the center. That is YC. Now, as we have calculated, is equal by using the shear force and bending moment concepts are required here. The prerequisites to understand the deflection of the beams is thorough understanding, thorough knowledge of shear force diagrams and bending moment diagrams. Next, bending moment, bending stresses distribution or bending stresses variation along the section, bending stresses distribution. In the bending stresses, one has to understand the thorough understanding. One has to know the knowledge of theory of pure bending. Now, from the concepts of shear force and bending moment diagrams, now here from the shear force sign conventions, we calculated here what are the reactions at support A and support B. That is RA equal to RB, that equal to W by 2. Why RA equal to RB here? The load is acting at the center. That load is shared by two supports because at equal distances are there, so that the reactions are equal. That is RA equal to RB. Now we are considering a section X, capital X, at a distance of small x from support A. The bending moment at this section is mx, that mx equal to RA times x. What is that RA? That is W by 2 times x. So it is the point load. There is no loads here. That is the positive bending moment here. That is why positive sign, left portion in clockwise direction. That is the positive bending moment mx. That is W by 2 times x. But we know the bending moment at any section. The equation, that is m equal to ei times d square y by dx square. At x, what is that x is? W by 2 times x, mx, equal to ei times d square y by dx square. Mx equal to W by 2x, substitute here in the equation, that is W by 2x equal to ei times d square y by dx square. Now, we know that equation, that ei into d square y by dx square equal to W by 2 into x. Now, first integrate first. First integration. Integrate this equation once. That becomes a slope equation. Ei into dy by dx equal to W by 2 into x integration, that is x square by 2 plus c1. This is the equation of, which equation here it is? This is the slope equation. The c1 are to be calculated by using boundary conditions. So the boundary condition is that constant of integration. that is at x equal to L by 2, at x equal to L by 2, whatever slope here, there is no slope. The slope, if you draw a tangent, what is the tangent? The angle, the slope becomes 0. There is no slope. The slope dy by dx equal to 0. Why? Because the maximum deflection is taken place at the center. Where maximum deflection is there, the slope is 0. So at the center of a simply supported beam is 0. Substitute this boundary condition in equation 2 here. Then ei into dy by dx slope is 0, that equal to w by 2. What is the x equal to L by 2? That is L square by 4 by 2, L square by 8. That w L square 2 times 4, 4 into 4, yes. That is plus C1. The C1 equal to minus w L square by 16. Substitute this C1 value in equation 2. Then you will get it. That is ei into dy by dx equal to wx square by 4 minus wl square by 16. This is known as the slope equation. By using this equation at different lengths, at different distances of the length of the beam, suppose if x equal to L by 3, x equal to L by 4, x equal to L by 8, x equal to L by 10, we can find out the value of the slope wherever wherever we want required. So this is the source equation for calculating the slope of simply supported beam subject to point load at the center. Now slope is maximum where? At A. Then slope is maximum at A means whatever x value is 0. And also slope is maximum at B. Then it becomes x equal to L. Substitute here. Then we will get it, the value of the slope, maximum slope. So by substituting this in this equation x equal to 0, then what happens? Slope ei into dy by dx equal to minus w square by w L square by 16. That is w L square by 16 ei. That is theta A. Why negative sign here? It is indicating the slope at A and the slope at B are equal. At B we want x equal to L. If we substitute in the equation 3, we will get it WL square by 16 EI. So it is the downward direction. So the negative slope, that's theta, negative value indicates. So this equation theta B equal to theta A, that is slope in radians. Now so far we have covered what is the slope. Next, second part, we need deflection. This equation of the deflection. So derive, again integrate the equation, the slope equation. Where is the slope equation? Integrate the slope equation of equation 3. This equation, then we will get it what? We will get deflection equation. Then the equation 3 we are doing ei into y equal to wx cube by 12 minus wl square by 16x plus c2. The c2 is the constant of integration. It can be calculated by using boundary condition. The another boundary condition where at x equal to 0, what is the deflection? 0. So at x equal to 0 and y equal to 0, substitute in this equation. Then we will get it the constant. That becomes C2 becomes 0. Substitute this C2 value in this equation. Then the equation of the deflection is ei times y equal to wx cube by 12 minus wl square by 16 times x. Or in terms of y, wx cube by 12 ei minus wl square by 16 times x ei. Or 1 by ei times wx cube by 12 minus wl square by 16 times x. This is the deflection equation. Now wherever we need throughout the span, by substituting different values of the x, we can find out we can find out the deflection of the beam. X equal to L by 2, substitute, then we'll get the maximum deflection. At x equal to 0, y equal to 0. At x equal to L by 4, x equal to L by 2, L by 3. Like that, if you substitute various values of x length, we can get it, the deflection of the beam. So this equation is known as the deflection equation. Okay, that's what here from this equation we can find the deflection at any point on the beam by substituting the values of x. The deflection is maximum at the center at where x equal to L by 2. Then after substituting x equal to L by 2, that is EI into YC center, that is W by 2, that is x equal to L by 2 cube minus WL square by 16 times x equal to L by 2. Then WL cube by 2 cube, that is 8, 12 into 8, 96, 12 times 8, 96 minus WL cube by 60 times 2, 32. After doing LCM, that is 90 here, LCM, that is WL cube minus 3L cube by 96, that is minus 2WL cube by 96, that is WL cube by 48. So YC equal to, that is EI into YC equal to minus WL cube, negative WL cube by 48. Then YC equal to negative of WL cube by 48 EI. So why negative sign? This is deflection is downwards. Deflection downwards negative. The deflection is upwards, it becomes positive. Now deflection is downwards, that's why negative. So deflection, downward deflection at the center of the beam, YC equal to WL cube times 48 EI. This is important equation. What is the slope? Slope equal to WL square by 16 EI. Slope WL square by 16 times EI. These are the derived formulas or derived equations for the case of simply supported beam subject to point load. For this case study only. Again, if the case is the load is with the different at the center at x equal to L by 2, the L by 2 distance. If it is going away from that, then again changes. Equation will be changed. Okay. So the equations for this downward deflection, WL cube by downward deflection equal to WL cube by 48 EI, and another formula is that WL square by 16 EI, slope. Okay, WL square by 16 EI. These are the slopes where theta B or theta A. These are deflection is maximum, the maximum deflection of a simply supported beam subject to point load. Suppose, let us solve how to apply this formula in solving the problems of a simply supported beam. When a simply supported beam is subjected to point load W 10 kilonewtons at a distance of 2 meters from the left hand support of a simply supported beam. The total length of the beam, the total length of the beam is 4 meters. find the maximum deflection and slope at the supports. So here, how to start this problem? The point load is acting, the simply supported beam mentioned, and the point load is acting here. Where it is acting here, that is 10 kilonewtons, and it is acting from left hand support 2 meters, and the total of the length of the span of the beam is 4 meters. So make the supports A, B, and point load is acting at the midpoint 2 meters. And one more thing, the material of the beam not mentioned and the section of the beam also not mentioned. So here we'll get the values in terms of EIs. We'll solve both the cases considering the material of the beam and section of the beam. We consider the second problem, but here, so the maximum deflection takes place at the center. That is the formula that YC equal to WL by 48 times EI. What is W here? The load, which is 10 kilonewtons, that is 10 into 1000, 10,000 newtons. L is 4 meters, 4 cube by 48 times EI. So, after simplification, that is 10 power 4. So, 1/4 becomes 4 into 4 by 48 times EI. This 12 times, again, this is the 3 times. That is 4 by 3 into 4 by 3 by EI into 10 power 4. This is the YC. Deflection takes place. Now what about next? Slope. The slope takes place at the supports A and B. Substitute in the formula of WL square by 16 EI. Theta A or theta B both are equal. WL square by 16 EI. What is the W here? 10,000 newtons. What is the L value? 4 square by 16 EI. 4 square and 16 get cancelled. That is 10 power 4 by EI. This is the value of slope. And here, these are the values of deflection. This is the value of the deflection. If they consider material, property of the material, the modulus of elasticity of the material is 2 gigapascals or 2 giganewton per square meters. Our moment of inertia, that I is suppose is having a rectangular section of the beam. Considering the above problem, considering the above problem, the section of the beam, cross section of the beam is rectangle width B equal to, consider it as some 40 millimeters, depth D equal to 30 millimeters, and the property modulus of elasticity, of the material of the beam is 2 giganewton per square meter. Then how to consider it? From this, we already calculated that Yc equal to, at the center, that is equal to 4 by 3 times 10 power 4 by Ei. Substitute here. What is the E value here? E value is 2 times. We considered 4 meters in terms of meters. Yes, E value. So here we have to consider E 10 power 9. I value. Here it is, the I is BD cube by 12. Convert is in millimeters, that is 40 into 10 power minus 3. What is the D? 30 into 10 power minus 3 whole cube by 12. Substitute this value of the I here, and deflection at the center will be obtained. And what is the slope? The slope is 10 power 4 by Ei. The slope equal to theta A or theta B equal to 10 power 4 by Ei. That is 10 power 4 by, what is the E value? 2 giganewton per square meter, 2 into 10 power 9. And I value, what is the I here? BD cube by 12, 40 into 10 power minus 3, 30 into 10 power minus 3 BD cube by 12. So after simplification, we get the value of the slope. So in this manner, we have to apply the formulas, that is a slope and deflections in the problem, solving the problems. Here we consider the model based on the data, that is simply supported beam subjected to point load at the center. The method we applied here, which method we have applied here? We have integrated 2 times, that is the double integration method we considered. The double integration method and moment area method are applicable for single loads, whereas Macaulay's method are useful for calculating when the beam is subjected to multiple loads. Here we applied double integration method and derived the equations for both slope and deflections. For slope it is WL square by 16 EI. For deflection it is WL cube by 48 EI. And calculate the problems by using those formula, those equations, and solve the deflection at the center, maximum at the center. What we have calculated here, the maximum deflections and maximum slopes. For a simply supported beam, maximum slope is at the supports and maximum deflection is at the centers. So we calculated here the deflection, maximum deflection and maximum slopes values, and applied those equations for solving the problems for the given data. So let me summarize what you have done here. Now in this session, we have calculated methods, various methods, under the introduction of 3 methods, that is double integration method, second method is moment area method, and the third method is Macaulay's method. And we studied the double integration method derived for the case study of a simply supported beam subjected to point load at the center. And we derived the equation, or we found the slope and deflection equations derived and applied in solving the problem. And the references we followed here for this session is, as usual, we followed the textbooks, reference books and web references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.